Good morning, sir.
Yeah, good morning. So, are there any questions, doubts?
No, sir.
Okay. So, okay, then let me start. I think attendance is poor, and this is the basically the very important class. I'm going to start finite element, essentially how the element level governing equations are developed. So, if you can call your other friends to join, that would be nice. So, yeah, let me start. So we were talking about development of element level governing equations. So I had highlighted all the steps involved. Development of element level governing equations. So I am going to take different elements and demonstrate that. So first the element I am going to take is a truss element, and this is 1D element, basically one dimensional element. So essentially the problem, we have, of course, the boundary conditions can be anything, but the problem we have done earlier, so it's the same. For this we want to develop now the finite element. So say this is the rod, and it could have different boundary conditions. The properties might vary. So what I'm showing a schematic, simple schematic. So this is the x direction, and in this direction the displacement is u, and there is a distributed force along the length. Say for example, no torpedo, maybe you can model it as a one dimensional using one dimensional element, where the if basically the effect of radial pressure is ignored, and only the drag forces and those are considered in the deformation. So this is the force q, and the length is l. So here if you look at the u, basically for this to be idealized as one dimensional truss element, the cross sectional dimensions have to be much smaller compared to length l. So that is the main thing, and we will see that in this case there is only one unknown variable, that is u. Use the displacement along x direction. So this is the displacement along x direction, that is along the length. And you will see that this is the only unknown field variable. This is the only unknown field variable, and it's only function of only x coordinate, that is x, and x we call it as independent variable, which is the range of x is known. So the first step, as we had said, was the discretization. So essentially what we are doing is just we are modeling the length. So we will model the rod by a line. So this is the line, and we discretize this line into a number of elements. So let us say a certain number of elements. So these are the nodes denoted by circles here. and these are elements. So element 1 is defined between node global node 1 and 2. So inside the circles I am putting the element numbers. So this is 2, this is 3, this is 4, this is 5, and this is 6. So see, these are node numbers. As you see, these 1 2 3 4 5 6, so without these circles. So these are node numbers, and there are other global node numbers, and the top what I have written, these are the element numbers. And now we want to develop the element level governing equation, so we consider only one particular element. So right now, like I have shown, is the 6 elements. So we consider one particular element. So say consider eth element. So e can be 1 2 3 4 5 6. And for this element, let me draw the free body diagram. So if I consider eth element, so this is the element. Now this is not the entire structure what is shown here, this is only one particular element. So in the element, now we will have it is defined between nodes. So we will have connecting nodes 1 and 2, and this is and the length of the element is, let us say, small l, which is no, obviously when you discretize the the total this rod into n number of elements, so the element length is small l would be equal to capital L divided by number of elements. And if you look at the coordinate system, so this is we take as the now local coordinate system, so that is actually capital X. So this coordinate system is capital X, and in this direction, of course, the displacement is u. So X is a local coordinate system, and of course there is a distributed force. So that same q over part of this. And since this element is taken out from this structure somewhere, here either, or if you take here, so there are going to be forces exerted by the left and right parts onto this element. So these are known as the cross-sectional forces. So on the right side, we will have the force, because I am denoting that Q2. This is actually EA into du by dx at this particular location. And let me put the superscript for the element number. So this is the eth element. So I'm putting it as Q2E. So there would be whatever structure is there on the right side of this will be exerting a force Q2 into E, and whatever structure is there on the left side, that force is subscript is here the basically node number, and superscript is the element number. So this is going to be the actually no force. And if you look at here, this capital X will be equal to 0 here, the capital X will be equal to small l here. And additionally, there are nodal displacements. So at this point, node 1, let us say the displacement is u1, and at node 2 the displacement is, let us say, u2. That is value of u at node 1, value of u at node 2. So and yeah, so this is basically the element. And here if you look at this 1 and 2, so they are different from these 1 2 3 4 5 I have written. So here, here this 1 and 2 are local node numbers. That is, one is first node, starting node, and the 2 is the end node of the one particular element. Local node numbers. So these are different from these nodes. So you can say these are the global node numbers. So they are different from this one, and two are the local node numbers. So, and if you look at the capital X, what I have used here is, so one was the small x here, which is the global coordinate having origin at the left end of the problem, and capital X is the local coordinate system having origin at the left end of one particular element. So for no element 1, let's say if you like take this discretization, the origin of capital X would be here. For element 2, the origin of capital X would be here. For this, origin of capital X would be here. For this element 4, it would be here. For element 5, it would be here. For element 6, it would be here, like that. So X is the local coordinate, with origin at left end of the element. So now if you look at for this element, earlier we have derived the integral functional for the whole domain, that is from small x equal to 0 to small x is equal to L. But now let's write the integral functional only for one element. So I'm going to write integral. We have already derived this, so I'm not going to show the derivation again. Integral functional, we also call it as total potential energy. Total potential energy functional, and we denote it by I. So I is equal to, first part is the strain energy. So only thing is now, because we are considering only this particular element, the element is domain is from capital X equal to 0 to capital X is equal to L. So the integration limit is 0 to small l and EA. And now because we have this x coordinate, so we are going to express u, the displacement, as a function of capital X. So we will know the derivative with respect to small x can be replaced by derivative with respect to capital X, because there is only shift in the origin. So du by dx, this is the strain and its square into dx. Now you'll have to keep in mind the difference between, I am using capital X now, which is the local coordinate with origin at the left end of no particular element. Then the potential of distributed force q, so displacement u into q dx. And then you also have to include the potential of these forces. So because now u1 is in the positive x direction and q1 is in the negative x direction, so work done would be negative, potential will be positive. So that would be q1 into u1. And if you look at these two are in the same direction, force and displacement, so the work done is positive, potential is negative. So we will have q2e into u2. So this is the integral functional. Now so we have already derived this, I am just using that. Only thing is writing only for one particular element. Now if you look at, we will have to, next step is, as I said, there is a assume an approximate solution within an element. So whatever approximate solution we assume, now the highest order derivative in the integral functional is the first derivative of u. So we will have to assume a approximate solution which is differentiable at least once. And then we will have to see the completeness requirement, and we also have to see the inter-element compatibility. So those are the three things I had discussed for the considerations for assuming an approximate solution. So now if you assume the approximate solution, so as I already said, this is within an element and not the entire domain. Entire domain is discretized into a number of elements. So what we are talking about is this approximate solution within an element. So this is within an element and not the entire domain. Earlier, like in approximate analytical solutions, we were assuming the solution which is valid over the entire domain. So now we will, whatever we assume, it should be differentiable at least once. So we have to have no minimum linear term, linear in x. And if we have linear from the completeness point of view, we should also have the constant sum. So a0 plus a1 actually x. So this is differentiable once, so it satisfies the differentiability requirement. And because we have the highest power of x as 1, so before that we have a constant term, so it's a complete polynomial. And the third thing we need to look at is the inter-element continuity. So as we have done, no, this problem is governed by second order differential equation, and for this the primary variable is u. So u has to be continuous across the elements, and for that u should be there as degree of freedom at the end node. So we already have u1 as degree of freedom at the left node and u2 as the degree of freedom at the right node. So these are the two degrees of freedom for the element as a whole, and with that we will be able to satisfy the inter-element compatibility. And corresponding to those two degrees of freedom, we have these two constants a0 and a1, so we can satisfy the inter-element compatibility requirement. And therefore this is the minimum we can know as an approximate solution we can assume. So now, as I already said, the primary variable is u, and this should be continuous across the element. So at each in nodes, and we are taking a two noded element, so each node having 1 degree of freedom, that is value of u, and therefore the element has 2 degrees of freedom. So two elemental degrees of freedom corresponding to two unknown constants a0 and a1. So we will be able to satisfy basically the inter-element compatibility requirement from this. And so the element, if you see, well, this is the element, the local node number 1, local node number 2. The local coordinate system is capital X, and the length of the element is small l. The value of u here is u1, and the value of u here is u2. So once we assume this is the minimum. Suppose no, you don't want to take a linear polynomial but a quadratic polynomial, then you can add one more term, and therefore you can have u as a0 plus a1x plus a2x square. But then you will have three unknown constants a0, a1 and a2. So corresponding to these three unknown constants, then you have to have basically three elemental degrees of freedom. So then you need to introduce an additional node, maybe at the center of the element. So there at each node you will have degree of freedom u. So you can have then u1, u2, u3 corresponding to three unknown constants a0, a1, a2. So we will be discussing that. That is, this is what we are having here is a linear element where the displacement within the element is linear function of capital X. So when we take a quadratic term also, that is known as the quadratic element. So we will be talking about that also. So now the next step in the finite element formulation is that we express the unknown constants, this a0 and a1, in terms of the values of variable u at node 1 and 2. So next step is express a0 and a1 in terms of elemental degrees of freedom. And so when the why the word degrees of freedom used here, because the once we know these two displacements u1 and u2, we will know exactly the deformed configuration where this element would lie. So we need these two parameters in u1 and u2. So therefore, and these are for the element as a whole. So they are referred to as elemental. That means for the element, and degrees of freedom is, if we know these parameters, we know the deformed configuration of the element. So that is why they are referred to as degrees of freedom. So now for this purpose, we have u is equal to u1. That is value of u at node 1, this particular node. U equal to u1 at capital X equal to 0. So if we put this now in this expression over here, so we will have u1 is equal to capital X equal to 0 means a0. So that is one equation. Second is u is equal to u2 at capital X is equal to L. That is value of u at this node is u2. So that will give you u2 is equal to, on the right hand side in this expression, it will have a0, you will have a0 plus a1 into small l. So now if you solve this equation, so you have u2 is equal to a naught is already u1 from here plus a1 into L. So you will be able to write this as u2 minus u1 upon L is equal to a1. So now once we have got no, a naught as u1 and a1 as u2 minus u1 by L. So we can put this in the expression over here. What we have got this one, and now if you put that, so you will have finally the approximation of the displacement u within the element in terms of, so a naught is u1 and a1 is u2 minus u1 upon L into capital X. So now what you can actually do is, what we do here is we collect the coefficients of u1 together and coefficients of u2 together. So if you look at this is 1 minus, here you will have u1 coefficient is x by L. So you can write it this as u1, and u2 has only this coefficient x by L into u2. So now once you have this, so we have some nomenclature over here. So this is the interpolation of the displacement within an element. That means, so what we do is, no, we refer to this as interpolation function. So this we write it as n1 into u1, and this we write it as n2 into u2. So here, as I have said, n1 is 1 minus x by L, and n2 is x by L. N2 is x by L. So now these basically are referred to as, these n1 and n2 are referred to as interpolation functions or shape functions. Interpolation functions are shape functions. Why this terminology? No, in this case they are also referred to as Lagrange interpolation functions. Lagrange interpolation functions. So why this terminology? Because you once you know u1 and u2, these are the values of u1 is the value of u at node 1, and u2 is the value of u at node 2. So if you know u1 and u2, then to get the value of u anywhere between the nodes 1 and 2. So this is the element, this is node 1 and this is node 2. And if you want to find out the value of u at any point between the nodes 1 and 2, then we determine that with the help of these functions 1 minus x by L and x by L. So that is why they determine the shape of variation of u between nodes 1 and 2 within the element. So are they are used to interpolate or find out the values of u at anywhere between the nodes 1 and 2. So that is why interpolation functions, because they are used to find displacement u anywhere between the node 1 and 2, or they are also known as shape functions because they determine shape of u variation along no element from node 1 to node 2. And if you look at here u1 and u2, so I have already explained u1 and u2 are the element node, each if you look at the u1 is a nodal degree of freedom, nodal degree of freedom. Similarly, u2 is also a nodal degree of freedom. When we put both together, u1 and u2 together, so that forms the elemental degrees of freedom, and they are nothing but values of u at node 1 and 2, the starting node and the end node. If you look at the n1 is 1 minus x by L, and n2 is x by L. So if you look at the plot of n1 and n2 along the length of the element, so this is the element node 1 and node 2, and this is the capital X coordinate. So if we plot here n1 and n2, these two functions. So if you look at n1, which is 1 minus x by L, so we put x equal to 0, then it will give you 1. And if you put x is equal to capital X is equal to small l, it will give you 0. And in between, it's a linear function of x, so it varies linearly. So this is the variation of actually n1. So unity at no, this value is unity over here. So unity at node 1 and 0 at node 2. If you look at n2, At capital X equal to 0 it is 0, and at capital X is equal to L it is unity. So if you look at no the this say function will be this like this. So this is unity over here. So this is the plot of shape function n1, and this is the plot of shape function n2. So now, now this approximation what we have here, I want to express this in terms of uh, product of vector and matrix and vector. So I want to write this as n1 into n2, and that side the vector u1 into u2. So I'm what I'm going to do throughout this course, I will denote matrices by this square brackets and vectors by curly brackets. So this is the notation I'm going to use. Although in this case you will see that this n1 n2 is forming a basically a row vector, but in general no, when we have more number of variables and so on, so this can be a matrix. So I'm still using the matrix notation for this. And this the right side what we have is it is always going to be the vector of elemental degrees of freedom. So we will always be arranging that as a vector. So I'm using this notation. So this is 1 by 2, no, the matrix, and this is a vector 2 by 1. That is one row and two columns over here, and two rows and one column over here. So this is known as interpolation matrix. It is given a notation, so I will be talking about know that notation. And this is I know is a vector of elemental degrees of freedom. Vector of elemental degrees of freedom. So we can write this as use the notation. So this is known as h, and the other vector we write it as de. So basically if you see where h is this n1 in n1 and n2, and de is the vector of elemental degrees of freedom. So this is the interpolation matrix, and this is the vector of elemental degrees of freedom. So d is nothing but basically u1 and u2. So this is the notation. H is interpolation matrix and d is the vector of elemental degrees of freedom. So interpolation matrix means because it is consisting of interpolation functions n1 and n2 are shape functions. So that is why that name, and d is the vector of elemental degrees of freedom because it is involving the unknown displacement at nodes of all the nodes of the element. When we ultimately see we have to substitute this approximate solution in the integral functional, so we need the derivative of u. So now if you look at let me call this as equation 1. So we differentiate equation 1. So what do we get? So differentiating equation 1, we will get basically as you see du by dx is equal to this side we will have dh by dx, and into this side is u1 u2 which is actually de. We are differentiating equation 1, and as you know this dh by dx, because h is consisting of n1 and n2, so this will be actually dn1 by dx and dn2 by dx. So please keep in mind that no, these are the two elements of this matrix. This is not product dn1 by dx into dn2 by dx. This is one first column, this is the second column of the matrix into de. And in the finite element terminology, this derivative matrix derivative of shape functions or the derivative of interpolation matrix is known as strain displacement matrix. So we write this as b and into de. So where no this basically if you look at the uh, b, so b is nothing but no this matrix dn1 by dx, and this is dh by dx actually. So dn1 by dx and dn2 by dx, and it is referred to as strain displacement matrix or gradient matrix. Because it is why it is referred to as a strain displacement matrix, because du by dx no, this is as you know the strain epsilon xx. So it is giving us the relationship b matrix. Through b matrix we are getting the relationship between this strain du by dx, and the vector of elemental degrees of freedom d, which is a displacement vector basically. So that is why this is known as strain displacement, strain displacement matrix. Or say for example heat transfer fluid mechanics problems, we call this as a gradient matrix. So now from this you can also write, if you want to write du by dx transpose, so that would be b into de whole transpose, not the square, transpose. So superscript t I am using for transpose. So as you know, the if you have two matrices and their products, so the transpose would be second matrix transpose into first matrix. So this will become de is superscript over here, d transpose into b transpose. So that is what no you will have. And so now if you look at the epsilon xx, as I was saying, the normal strain along x direction, epsilon xx will be equal to du by dx. And du by dx is, now you see, because now if you look at n1 and n2, n1 is, we have seen here, n1 is basically 1 minus x by l, and n2 is x by l. Their derivative dn1 by dx would be minus 1 upon l, and dn2 by dx would be 1 upon l. So they are constant independent of capital X. So when you get this strain du by dx epsilon x equal to du by dx, which is b into d, since b is constant, so it gives us the constant strain within the element. So is equal to, this is no b into de, and this is constant within the element, constant within the element. So within each element the strain and therefore stress are going to be constant based on this element. So once we have done know this, then we go for the, now we have to we need some equations. So here the problem is, so far we have these unknowns u1 and u2. So how do we get equations for finding out u1 and u2? So those equations we can either know directly use the Galerkin method big form, and from there we generate. So now there are two unknowns in this whole interpolation. If you see, the two unknowns are u1 and u2. So we need these no two equations for finding out u1 and u2. So one way is that, no, use the Galerkin method and take the weight functions as one weight function w1 is equal to n1 and w2 equal to n2, and then no, from the weak form you develop those two equations. The other is we substitute this approximate solution in the integral functional and minimize the integral function. So we basically use Rayleigh's method to find out, no, set up the equations for finding out u1 and u2. So I'm going to use this Rayleigh's method. So based on the integral functional. So now because we are going to substitute no, these approximations, so that is u is equal to h into de, and we have say this du by dx is equal to b into de. Say, let us say this is equation number 2. So we want, now these two are giving the u and du by dx as a product of matrices and vectors. So we have to rewrite the integral functional so that the matrix vector products are consistent. So now if we look at the integral functional or total potential energy functional, integral functional are, as I have already said, total potential energy functional. So the term I have already emphasized, no, not a function, it is functional, because u is a function of x and then I is a function of u. So it's a function of function, and that is why functional. Functional means function of function. So now if you look at I is equal to half integral 0 to small l, and then we have EA, and then next term is du by dx whole square. Now du by dx whole square, what I can do is I can write it as du by dx transpose. So this is a scalar, so its transpose is going to be the same thing. into du by dx. I can write it like this. This is nothing but du by dx whole square, but we are splitting it into two terms, du by dx transpose into du by dx, so that when we write du by dx as b into de, matrix multiplication would be consistent. So we are writing it like this. So this is the integration. The second term is potential of the distributed force q. So that was u into q, and that we are writing as u transpose into q. And the purpose of writing here u transpose is so that in this term also the first one is transpose, this is also transpose, so that left side we will get d transpose common. So that is why we are writing it like this, dx. And the last term in the integral functional, so this is your integral functional what I have written over here. So this is the last term. This also I want to write as a product of the force and the vector of elemental degrees of freedom. So therefore no, the last term can be written as minus, and then u1 u2 transpose, and then we have minus q1e and q2e. So if you multiply, no, you take the transpose u1 u2 transpose. So right now it's a column vector. When you take the transpose, it will become row. So you will multiply with this column vector, you will get basically no q1e into u1 minus q2e into u2. So it will give you the same what we have already written. So now if you look at, we substitute the approximation for du by dx and u in this integral functional. So we will have half integration 0 to L, and then you have EA. And now you see du by dx transpose. So I think I had written here, I already explained you that du by dx transpose is ultimately d transpose into b transpose. So little bit of matrix operations you should know. So we will have du by dx transpose as d transpose into b transpose, and then again we have this du by dx. So du by dx is basically b into de dx, the integral, and then minus integral 0 to L you have, and then u transpose. So similarly u transpose will be d transpose into h transpose into q dx. So this, and then of course this is nothing but your de vector of elemental degree of freedom. So we can write that as d transpose, and this is minus q1e and q2e. So this is the integral functional after substituting the this approximation for whatever we have got u and du by dx. So when you substitute this, so hello, am I audible? Yeah, I think if I know, please ask questions in between. Hello, am I audible?
Yes, sir.
Yes, sir, you are audible.
Okay. So now this is the integral functional we are getting, and see, the purpose is ultimately to get the two equations, so that now we have equations for finding out e1 and e2. So that's the purpose. So we are trying to substitute this in the integral functional, and then we are going to minimize that integral functional. So now what I can actually do is can rewrite little bit on this. So of course there is a no, some mathematics. It's although simple mathematics, but it's there and you have to follow this. So half integration 0 to L, before me. Yeah, so what I want to do is this D transpose. If you look at in general, although in this particular case B is also independent of X, so it is constant, but in general no, this B could be function of the capital X coordinate. So that I'm going to keep it inside the integration. But no, as far as this d is concerned, since this d is the values of u at nodes, so those are always going to be independent of the x coordinate. So we can take this out. So we will take this on the left hand side and this on the right hand side. So I can write half de transpose and then integral 0 to L. In general, E into A, the Young's modulus into cross-sectional area, could also be function of X. Suppose if you, for example, consider torpedo and idealize that using these truss elements, so the cross-section of the torpedo is going to vary along the length. So then Ea would be function of x. So D transpose we have taken, this is anyway scalar. So this D transpose I have taken on the left hand side, and then here you have B transpose into B and then dx. So because no this whole quantity is going to be in general, no, this Ea could be function of capital X, B could be function of capital X, so they have to be inside the integration sign. But the D, since the value of u at node 1 and 2, that can be taken out of the integration sign. So I have taken D transpose on the left side and D on the right hand side. Then similarly in this term I can take no this DE transpose out of the integration sign, and then we will have integral 0 to L H transpose into Q dx. And of course the last term is anyway it's a D transpose into minus Q1E and Q2E. So I think I have already told you that 1 and 2 here sub in Q, capital Q, the subscript 1 and 2 are the node numbers and E is the element number. So now if, what I can do is denote this. This is nothing but actually the stiffness matrix of the element. So this is what we call as the stiffness matrix of the element. This is the load vector which we call as no the external load vector, and this is the internal load vector. Why internal? Because this is coming from the forces exerted by the adjacent elements, no. So when you take earth element, there would be E plus 1th element on the right and E minus 1th element on the left, so they are exerting forces on this. So this is the force exerted by E minus 1th element on the left, and this is the force exerted by E plus 1th element on the right. So this is known as internal force vector. So I'm going to use use some notation for all these. So we can write half of D transpose, and then this I'm calling as the Ke, this whole quantity, and then we have this D, and then minus we have this DE transpose into F external, and superscript E is for the element, that this is for the element. No, this superscript is element. So F external is this quantity is F external, and minus we have this DE transpose into this I am calling as F internal for the element. So F internal is this is F internal. So we are defining these quantities over here. So now let me define them. So where Ke which is given by this integral 0 to L E A B transpose into B dx. So this is known as the element level stiffness matrix, or simply elemental stiffness matrix. So this is because this is for one element, so therefore element level stiffness matrix, or sometimes we simply call it as elemental stiffness matrix. Elemental stiffness matrix. So similarly this F external which I have used over here, F external is integration 0 to L, we have H transpose into Q dx, and this we call as element level external load vector, or elemental external load vector, elemental external load vector. And no the finally this notation F internal is basically this minus q1e and q2e. This is elemental internal load vector, or element level elemental internal, not external, internal load vector. So yeah, so this is now we have called here the stiffness matrix, defined the what is the stiffness matrix of the element, what is the external load vector, what is the internal load vector. So all these quantities we have defined, but now, still we haven't got two equations for finding out u1 and u2. So how do we get those two equations? So we have seen when we had derived this integral form, so when we came from the big form, we had delta I equal to 0. So essentially we want to find out u1 and u2 such a way that we satisfy the differential equation. So we can say the solution of the solution of original governing differential equation and the governing differential equation we have already derived. So for the element label would be d by dx ea into du by dx plus q equal to 0. So this is the governing differential equation. So the solution of original governing differential equation is equivalent to delta I equal to 0. So the basically we are going to generate the equations for finding out u1 and u2 from this variation of I equal to 0. So now if I write the expression for delta I, so now delta I, if you look at I is now the defined over here. So this is now we will work with this I what is defined over here. So now if you look at, we have to take the variation of the first term, and the variation is taken for no of an unknown quantity. So if you look at this ke is a known quantity, integral ea b transpose b dx, so that would be a known quantity. So only unknown is this vector d, and d is appearing on the left side and also on the right hand side. So we can use the similar to different derivative of product of two functions. We will use the same approach for writing out the delta I. So we will have half and then the variation of first term. So delta of
Excuse me.
d transpose. Yeah, yes, please.
Sir, can you please repeat this last thing which you have told, the solution of original governing differential equation?
Yeah. So see, what I was saying is basically this is the governing differential equation for the problem. So we have already derived that. Only thing is right now what I have written over here is for the element, and from this equation we have written the weak form, and then we had written w weight function as delta u, and then we had got delta I equal to 0, if you remember. So you can say that the solution of original differential equation is equivalent to delta I equal to 0. So essentially in the limit when we have approximate solution with sufficient number of terms, or the finite element approximation with sufficient number of elements, so whatever solution we get by solving this differential equation will be same as whatever we get the solution from delta I equal to 0. So I am saying here the solution of original governing differential equation is equivalent to delta I equal to 0. uh, Essentially whatever solution we are saying, I'm saying that whatever solution we get from this differential equation, same solution we will get from this delta I equal to 0. So we solve this. So rather than now substituting this approximation u equal to h into d in the weak form and then taking weight functions as n1 and n2 and setting up two equations, I'm directly putting it in the integral functional and taking delta I equal to 0, and from that I'm going to develop the element level governing equation. So this is what I'm doing. Okay, is that clear? So
Yes, sir.
yeah, so essentially it is saying that if you solve the differential equation, and whatever equations you get for u1 and u2, you will get the same equations from this expression delta I equal to 0, because we have identified I from delta I equal to 0 only. So from the differential equation, then weighted residual statement, then the big form, and then in the big form w equal to delta u, and then delta I equal to 0. So we are continuing the same thing over here. So now delta equal to half delta D transpose, and then we have this Ke into D, they remain as it is, then plus half, now the variation of the second term. So we will have this D transpose into ke into delta of de. So we are using the product rule, no? So variation of the first term into the second, and plus then we have the first term into variation of the second. So from the first we will get these two, and then we will have the second term. If you look at the in this I, so this is d transpose into f external. F external is a known quantity, so we will take only the variation of d. So that would be minus delta of de transpose into f external. And similarly, the third term would be delta of d transpose into f internal. And now this should be equal to 0. Delta I should be equal to 0. So the weak form is equivalent to delta I equal to 0. Now if you look at, so we want to do little more here. So now if you look at, although these terms look like two different terms, this is one term and this is another term, but if you look at ke is at size 2 by 2. Why size 2 by 2? Because if you look at, here we have defined ke. So E is a scalar, Young's modulus into cross-sectional area, that is constant. B we have seen it is a 1 by 2. So that is one row and two columns. So B transpose will become basically 2 by 1. So when you multiply this 2 by 1 with 1 by 2 matrix, you will get a 2 by 2 matrix. So you will see this K is a 2 by 2 matrix. So this is a 2 by 2 matrix. D is a, if you look at 2 by 1, and then d transpose will become, because d itself is 2 by 1, its transpose will become 1 by 2. So we will have this one as, yeah, d transpose is going to be 1 by 2. So as a whole, this is a quantity as a whole, it is a scalar. So if you multiply all three together, delta d transpose into k into d, it's going to be a single number, so it's a scalar. Similarly, if you look at this, also is d transpose 1 by 2, k is 2 by 2, and delta d is also 1 by 2 by 1. So if you look at this one, it is also 2 by 1. So it's a scalar. So now what I want, because I have in this term I have delta d transpose on the left hand side, here also I have delta d transpose on the left hand side. So same thing I want to do for these two terms also. In this anyway I have delta d transpose on the left, so I can take that common, but this term I want to rewrite. So since this term is a scalar, because 1 by 2 into 2 by 2 into 2 by 1, finally we'll get 1 by 1, that is a single quantity, a scalar number. So we can replace by its transpose. So what I'm saying, in this delta I expression, the second term can be replaced by its transpose. Because why? Because as a whole it is a scalar. Scalar means a single number. So if we do that, so I can write then delta I equal to half the first term as it is, delta of d transpose into ke into de. So that remains as it is. The second term I am going to replace by its transpose. So when I take the transpose of this, so this is a product of three matrices. So you will have the, if you have say product of three matrices ABC, so ABC whole transpose would become C transpose, B transpose, A transpose. So the last matrix will come first and the intermediate would be at the intermediate location, and the first one will go to the last. So that is what will happen. So if I replace this term by its transpose, so I will have first this will be coming, so we will have plus half is anyway there, and then you will have delta of DE transpose and then you will have no this ke transpose. Actually, as I said, no, if you have product of three matrices ABC whole transpose, so essentially I am making use of this. No, if you have ABC three matrices and their transpose, that would become C transpose into B transpose into A transpose. So this is what comes. No, this no, in the matrix, if you have the my product of three, it would be like this. So the same thing I'm applying here. I'm replacing this term by its transpose, and when I'm taking transpose, so because this is the last term, it will come first, and it's transpose delta D transpose. Then we will have Ke, Ke transpose, but Ke is a symmetric matrix. So the transpose of a symmetric square matrix will be the matrix itself. So K transpose would be equal to K. So I'm writing that as K. And then finally you will have this D, this D transpose. So it would be D transpose transpose. So transpose transpose will become simply DE. So finally we will have this D over here, because no the this is the first term will go to the last. So D transpose transpose. So if I have a matrix A transpose, its transpose would be simply equal to A. So I am making use of this result, that ABC transpose equal to C transpose B transpose A transpose, and A transpose transpose is A. So you'll actually get this term minus, of course, delta D transpose into F external for the element minus delta DE. So these terms remain as it is. F internal for the element is equal to 0. So now, once we have done this, so we can write delta I equal to, now these two terms are exactly the same. Now you can combine these two together. So I can write that as half will go, because this half plus half will go. So we'll have basically delta of D transpose into KE into DE, and minus delta of D transpose into F external for the element minus delta of D transpose into F internal for the element is equal to 0. So this is what we will have. Now you will see that I can take delta D transpose as common. So I can write delta I equal to delta of DE transpose as a common. So when I take delta D transpose as a common, so I will have here this as Ke into D. This is what I will have. This term would be simply minus F external for the element. Then we will have minus F internal for the element. And this whole thing will be equal to 0, of course. So now what we do is, so now see, this delta is now product of two things. One is this delta D transpose, and another is this whole quantity. So now for if this has to be, delta I has to be 0, because we are solving the differential equation, and the solution of differential equation is equivalent to delta I equal to 0, or the differential equation is itself equivalent to delta I equal to 0. So we will have to equate this to 0. But then how? So it's a product of two terms. So there are three possibilities. Those three possibilities are that this either delta D is a null vector. That means all the elements of this are actually 0 0. So then the product would be 0. So that is one possibility. Second is that this as a whole is a null vector. That means when we take KD minus F external minus F internal together, so all the elements come out as 0 0. Then also we will be having it as 0. And the third possibility is that both of them are null vector, and therefore the product would be equal to 0. So these are three possibilities. But now as far as this delta D is concerned, as per the variational mechanics, this delta D is arbitrary. Arbitrary means no, we should be able to equate, no, we should equate delta equal to 0 for any arbitrary value of delta D. So if delta D is arbitrary, so one thing is that it cannot be a null vector, because for any other value of delta D, set of values delta D, we should we should have this expression equal to 0. So obviously this is cannot be a null vector. And then it is arbitrary means it should be 0 for any different set of values of delta D. So if it has to be 0, this product has to be 0 for different set of values of delta D, arbitrary set of values of delta D. then only possibility is that for this delta I to be equal to 0 is that this should be equal to 0, and that is what gives you the element level governing equation. So since delta I has to be 0 for any arbitrary delta DE, therefore no there we get this expression KE into DE minus F external for the element minus F internal for the element is equal to a null vector. Right now it's a vector because now if you look at this is a 2 by 2 matrix, this is 2 by 1 vector. When you multiply you will get a 2 by 1 vector. This is already a 2 by 1 vector, this is already a 2 by 1 vector, so this is 2 by 1 null vector, that is it is 0 0 0, it's a column vector 0 0. So then this has to be a null vector. This is a, as I said, it's a null vector, and this is what gives so finally you write the element label governing equation as Ke into De, and the load vectors you take towards the right, so F external for the element plus you have F internal for the element. So this is what is referred to as the element label governing equation, and this is what we wanted to actually derive. So this is known as now as you see, this is the stiffness matrix. I have already explained you, this is the vector of elemental degrees of freedom, this is the external load vector, this is the internal load vector. So the stiffness matrix into displacement vector gives you the restoring force, and that is balancing the external force and the internal force. So you can say that this is the basically the balance of forces, internal and external forces, and we call this as element level governing equation. And now if you so you may be thinking D is u1 and u2, so maybe you could get a thought process that can we solve this equation for u1 and u2. So the answer is no, although these are the equations governing the values of u1 and u2, but we cannot solve this. Why? Because to solve this you need the Ke inverse. I mean whatever method you use, but equivalently you need Ke inverse, and K is a singular matrix as it is for the element. If you look at it's a singular matrix, so you cannot solve as it is, right? This equation, but what you have to do is you have to assemble the number of elements, impose the boundary condition, and after the imposition of boundary condition then you can solve the resulting equations for the values of displacements at node points. So right now if you look at this K is going to be a singular matrix. Singular means its determinant is 0, so the inverse will not be possible. And now so once we have got this element level governing equation, so now let's look at for a specific case what are the structure of this matrix Ke and vector F external E. So let's look at that. So for I am going to take as, so now you see if you look at if you look at the definition of Ke, so Ke we have already said as integral 0 to L Ea B transpose B dx. So in that Ea could be any function of x, whatever way it varies. Of course, you need to know that function, and you can put that function and carry out the integration. So you will get the stiffness matrix. So that is not a limitation, but I am just assuming no Ea to be constant within the element and trying to derive the form of the stiffness matrix Ke for this specific case. So if Ea is constant, although it's not necessary as far as the finite element method is concerned, it can handle any variation of Ea, any function of Ea as a function of x. But if Ea is constant within the element, then we can write no this ea then can be taken out of the integration sign because it is constant within the element, it is independent of capital X. So I can take it out of the integration sign, and then we will have integration 0 to L, and then you will have B transpose into B dx. If ea was a function of X, then you have to keep it inside, put multiply everything, and then integrate each term of the matrix. So you will get ea and then integral 0 to L. So B transpose, if you see, it is B is dn1 by dx, dn2 by dx, basically a row matrix. Its transpose would become a column. So we will have dn1 by dx and dn2 by dx. So this is B transpose, and then B is dn1 by dx, dn2 by dx, and dx. So now if you multiply this, we get ea integration 0 to L, and the multiplication, no, that this into this will be the first row and first column. So we will get d1 by dx whole square, and then this into this will be the first row second column. So we will get dn1 by dx into dn2 by dx. Then the second row, so we multiply this with this, so we will get dn2 by dx into dn1 by dx, and then this into this, that is the second row second column. So dn2 by dx whole square integral dx. And now if you look at n1 is we have already defined 1 minus x by L. So dn1 by dx will be basically minus 1 upon L, and n2 we have defined as x by L. So therefore dn2 by dx would be equal to 1 by L. So if you put this values, so you can say finally that element double stiffness matrix Ke would be equal to Ea integration 0 to L, and then we have dn1 by dx whole square. So we will get 1 by L square, and this product will be minus 1 by L square, minus 1 by L square, and 1 by L square into dx. And now this is equivalent to, basically, in the matrix you have to integrate each element. So this is equivalent to Ea, and then integral, this is integral 0 to L 1 upon L square dx, and then integral minus integral 0 to L 1 upon L square dx. So you have to integrate each element of the matrix, minus 1 upon L square dx, and integral 0 to L 1 upon L square dx. So you have to integrate each element over here. So as you see, 1 upon L square is constant, so integral is going to be capital X, and then when you put the limit, you simply get L. So you will have basically Ea, and the first term would give you finally L upon L square, so 1 upon L, minus 1 upon L, minus 1 upon L, and 1 upon L. So now what you can actually do is you can take this 1 upon L common. So when you take anything common in matrix, so basically it will be coming out from all the elements of the matrix. And unlike determinants, in case of determinants, if you multiply the determinants, you multiply that constant to any one row or a column, but in a matrix you will multiply that to all the elements. So we can take this A by L common from all the elements, and we will have 1 minus 1 minus 1 and 1. So this is your stiffness matrix for truss element with constant A within the element. This is the stiffness matrix. So A by L 1 minus 1 minus 1 and 1. So this becomes the stiffness matrix. Similarly, now let's look at the load vector. So second thing is, if Q, the external load vector, so if Q is constant within the element, then we will have this F external for the element. Definition we have already given already. So you can take this Q is independent of a capital X, so can be taken out of the integration sign. So integral 0 to L, you will have H transpose into dx, H transpose into dx. So this can be written as Q integral 0 to L and then H is nothing but n1 n2 no, row vector, its transpose would become a column, so we will have n1 and n2 dx. And if you look at this q integral 0 to L, and we have, no, I can write, curly bracket, because now finally it's a column. So we have n1 as 1 minus x by L and n2 as x by L dx. So this would be equivalent to q, and then integral 0 to L 1 minus x by L dx, and integral 0 to L x by L dx. So now you have to carry out this integral. So finally, of course, now if you carry out the integration, so you will see that this first term would be integral would be x, and second would be minus x square upon 2L, and when you put the limits you will get basically L by 2. So you will finally see that f external for the element will come out as q, and here we will have L by 2, L by 2. So these definite integrals, when you evaluate, you will get basically these, and L by 2 can be taken common, so we will have QL by 2, 1 and 1. So this is the external load vector. There is another terminology in the finite element method, because no, this load vector which we have derived for distributed load Q using the shape function, so we call this as consistent load vector. So whatever we have got over here, so there is another terminology, this is referred to as consistent load vector. And there is another approach for, if you have a distributed force, so there is another approach where you can write the what is known as the lumped load vector. So now in this case what we are having is the no, this is the element, and this is the first node, and this is the second node, these are the local node numbers, and the distributed force right now we are taking a uniform distribute in load q is constant, means it is uniform. So the and the length of the element is basically L. So if you see that total load is going to be, this external load is going to be q into small l, and we equally divide, because there are now two nodes, so we equally divide this total load at this node and this node. So we will have ql by 2, ql by 2. So in this case you see that the consistent load vector is same as lumped load vector. So in this case, consistent means consistent with the shape function. So if you derive the load vector from shape functions, the way we have done over here, which came from the delta I equal to 0, that we call as a consistent load vector. So but in this case, consistent load vector is same as lumped load vector. As I already explained, you take the total load and equally divide between the nodes. So whatever you get is the lumped load vector. So the total load is q into small l. There are two nodes, so ql by 2 at each node, and therefore ql by 2 and ql by 2. So it will be same as this. So this is the the lump concept of consistent load vector and concept of lumped load vector. The next thing comes is the, so yeah, I think I want to stop here, and then I'll continue in the next class, because next thing what we need to do is we have discretized the the initial the domain into a number of elements, and we have developed the element level governing equations. Now to solve the problem as a whole, we need to assemble the element level governing equations of all the elements, and after assembly we will have to impose a boundary condition and then solve the equations, and that is where we will get the solution. So I want to stop here. In the next class, that is on Monday, I will talk about how to assemble, and then how to impose the boundary condition, how to solve the equations, and then how to do the post processing. And now if time is there, then I would start quadratic element. So this is a linear element, and that means the displacement u is a linear function of capital X within the element. So then I will talk about the quadratic element. So now if you have any questions and doubts, now you can ask. Yeah. So any questions, doubts? So anybody, any question, any doubt? Okay, so if there are no questions, I am stopping. Yeah, anybody want to say something? Yes? Okay, then thank you all for your attention. I'm stopping. I think I'm not able to hear if you, someone is trying to say something. Maybe you can ask in the next class if you have some doubts. So I stop here. Thank you all for your attention. Thank you. I'm stopping.